Hello, I am going to run through a quick description of this demonstration, and we're going to start up here with Doc 1, or Documentation 1, Part 1. The idea of this demo is to make a space-time diagram with two sets of 7 clocks. We've got a set of red clocks and a set of green clocks, and these clocks have paths marked by solid lines going forward in time. Positive slopes lines travel to the right and negative slope lines travel left. The clocks are presumed to be synchronized by Einstein's synchronization procedure in their own frames of reference. Okay, that means that in the reference frame where all of those clocks are deemed to be stationary, then they all tick simultaneously. The dashed lines down here represent the ticks. So -3, -2, -1, 0, 1, 2, 3. This is the event where the first clock ticks -3, -2, -1, 0, 1, 2, 3. And this is where the clock at x equals 3 ticks -3, -2, -1, 0, 1, 2, 3. And over here is the position where the clock at x equals -3 ticks -3, -2, -1, 0, 1, 2, 3. But anyway, they are synchronized by a process called Einstein synchronization procedure. The details of that are essentially that you use pretty intuitive methods to synchronize the clocks. Basically, you would send out a signal to the clocks to say, I'm sending out the signal now. Based on where you are with respect to this signal, set your clock. And so it's an intuitive procedure, even though it's called Einstein synchronization procedure. So the dashed lines mark the ticks of the clock, and the solid lines mark the paths of the clock. And that is the same for the green lines as well. And you can adjust the speeds of the clocks by moving that red dot. Sorry, that is not a red dot, that is a green dot, but this dot up here is red. Okay, changing trajectories, red clocks, green clocks, and U. Okay, by sliding the red dot along the upper hyperbola, you can change the trajectory of the red clocks, and by sliding the green dot, you change the trajectory of the green clocks. Finally, by sliding the purple dot, which isn't showing up right now, but there it is, there's the purple dot, you can change your own trajectory with respect to the space-time diagram. So when you change your own point of view with respect to everything, then all of this stuff moves. And that brings us to documentation 3, the transformation selector. The red selection dot allows the choice between Galilean transformation, Lorentz transformation, and the Tangerlini and inverse Tangerlini transformations. The Tangerlini transformations are offered, let's move that to Doc 3.1, issues with Tangerlini transformations. While the Tangerlini transformations are offered, there is a problem with the representation. Notice how in the Lorentz transformations, as I move the purple dot, the events of the green dots and the red dots kind of stay tied together. They don't scrape against one another. They transform without scraping against each other. But with the inverse Tangerlini, the green and red grids kind of scrape against each other. They don't maintain that. They don't transform quite properly. Same thing with the Tangerlini transformations. They don't transform quite properly. They scrape against each other. But with the Galilean transformations, they transform together. Nothing scrapes against each other. It's all very smooth. With the Lorentz transformations, also, the grids don't scrape against each other. It's all very smooth. Documentation part 4, the image positions. The purple dots and purple purple lines represent the locus of images observable at the origin, x equals 0, t equals 0. The coordinates of the events in the purple reference frame, in your reference frame, is found by simply reading off from the vertical and horizontal coordinate axis. So for instance, this event here, let me move it down a little bit. So this event here would be somewhere around -6 in time and +6 in space. This event over here would be somewhere around -3 in time and -3 in space. But if you look at the green grid, counting over on the solid lines, you get 1, 2, 3. You get the green grid shows it at about -2, yeah, 0, 1, 2, -2, and -2 on the time to 0, -0, or 0, -1, -2. While the red grid, well, it's not even inside the red grid, so it's past 3 and 3 on the red grid. But the different coordinate systems show this point at different locations, because you can check out, you can basically, actually I can fix that, so let's extend the red grid and the green grid a little bit. I'm going to do this by changing this thing to negative. I'm going to have it count from -5 to +5. -5 ... 5, and this go. I'm not sure that that's going to work or not. Yeah, actually it did work. I made it 5 for I equals -5 to 5. And with that, you can kind of see where things cross. Let me turn off the red. Make it so you just see the red grid. And you can see this point is at -4, -4. This point is also at +4, -4 according to the red grid. On the other hand, according to the green grid, let's turn the green grid on, turn the red grid off. And see, this event here is at -2, -2, and this event here, oh geez, it's way off. This event here, let's look at this event here, is at 1, 2, 3, 4, about -4.5, 4.5. So what am I trying to say is that the person that is on this world line, basically the purple observer who is traveling, is stationary, is seeing all 4 of these events, 1, 2, 3, 4 events here, and 1, 2, 3, 4 events here, and seeing these 4 events at certain coordinates in space and at time. Meanwhile, the green observer is seeing those events at a different position in space and time, and this one at a different position in space and time. And the red observer, or the red clocks, are measuring those same events to be at yet another set of coordinates of position and time. What do those let's see, 8 events look like from the red perspective? Well, move this to where the red is orthogonal, and you can see where they look like they are from the red perspective. What do they look like from the green perspective? Well, move this so that the green is orthogonal, and you see what it looks like from the green perspective. So you got 2 observers occupying this same point in space and time with different velocities can have different observations of where the events that they're located. They can disagree about where the events that they're seeing are actually located. Now I'll put those numbers back the way they were, so it just occupies the space between -3 and 3, and move on to Doc 5, length contraction. Okay, so this length contraction, I'm going to show it in both the Lorentz case and the inverse Tangerlini case. And time dilation is measured. Let's see. Let's move this. So we'll show what the green looks like. Okay, time dilation is measured between the dashed tick lines. Oh, I was going to do Doc 5 first. Sorry. Length contraction is measured along the x-axis. So this here is the x-axis. We measure from this point to this point. We look at how far apart the green or red clocks are in the purple frame. So from here to here, notice, is shorter than it looks like from the green frame. Here's the green frame from here to here, and from another reference frame, it looks like that distance from here to here is shorter. We are seeing where the green world lines intersect the horizontal line. Notice if we measured the length on the dashed tick line, if we followed this tick line all the way over to here, and then followed that same tick line all the way over to here, you would get a much larger distance. We would get a greater distance instead of a shorter distance. All right, now let's look at Doc 6, which is time dilation. And I'll slow that down a little bit, but time dilation is measured between the dashed tick lines along the solid world lines. So look here, here's a tick, 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 tick. So we can see that those ticks kind of stretch out as we move this down. The spacing between the ticks of the individual clock becomes a longer period of time, and that's called the time dilation. Notice if we measured along the vertical line from here to here, we would actually get a shorter time instead of a longer time. That would be like if I'm here and I'm watching the time on the clocks as they go by. So this is a different clock than this clock, and this clock is a different clock than this clock. So like the different readings on the clocks are actually different green clocks. But if you did look at those clocks, like several clocks instead of just one clock, you would get faster time instead of a longer time. I also wanted to show the length contraction and time dilation for how it's the same for the Tangerlini transformation. Notice right here the distance between, or the time between this event and this event, and we're going to see how that stays the same with the inverse Tangerlini transformation. So the time between this event and this event is the same amount of time as when I put it on Lorentz contraction between this event and this event. Another thing you can notice is that the Lorentz contraction, the space between this event and this event, is the same for the Lorentz transformation as for the inverse Tangerlini. You get the distance between this event and this event. So what the inverse Tangerlini transformation does is it duplicates the time dilation and the Lorentz contraction of special relativity, but it tries to preserve the what's it called, simultaneity. This, if you don't mind that it changes the speed of light, then that's all good. However, I find it kind of an empty philosophical question. People try to say that there's no physical difference between this particular diagram and Lorentz, but really I would say there is. In the Lorentz transformations, all observers see the same speed of light in all directions. With the inverse Tangerlini transformations, you're not seeing the same speed of light, and so that's not physically what people observe. We don't see a change in the speed of light. So I would not. I would probably throw out the inverse Tangerlini transformations on the account that we do not observe changes in the speed of light. And just to make the note here, the Tangerlini transformations is essentially it's the inverse of the inverse Tangerlini transformations, which means it basically does time undilation and length uncontraction. So essentially, this is the transformation you would use. The Tangerlini transformation goes supposedly from the lab frame to the non-preferred reference frame. And the inverse Tangerlini transformation goes from the non-preferred reference frame to the lab frame. So from the lab frame to the non-lab frame, and from the non-lab frame to the lab frame. So that's why they're different. One maps the events to the lab frame, one maps the events from the lab frame. But the Lorentz transformation says they're both perfectly valid lab frames, and there's no difference between mapping from the good one to the bad one or from the bad one to the good one. They're both perfectly equivalent. Okay, if you want to have a look at this demonstration, here is the link. I'm going to put a link to it in the comments under the video, or in the video description too.